Now, hello everybody. Now we are starting the second part of this vector analysis, and to be more specific, the algebraic the algebraic foundation of this vector analysis series in our electrodynamics video lecture. So here we are looking at the other operations on this vector. Okay, so this is which we call as the triple product. Okay, so triple product. So the name itself suggests that there in this operation we will use three vectors a, b, c. Let's assume a, b, c. So there are two type of triple product. One is the scalar triple product and the other is the vector triple product. So let's come to the scalar triple product first. So it is written in this way: a dot b cross c. Okay, so this is the scalar triple product because we are using the dot product over here. We are doing the dot product of a vector with the cross product of b and c. Okay, so what is the cross product of b and c? Well, it is the area. Let's say that this is the vector b and this is the vector c. So the cross product of these two vectors will be the area of this parallelogram. Okay, so this is going to be a parallelogram. So this is going to be a parallelogram. Okay, and this parallelogram, let's say that it is b cross c, which is, let's say, n vector. Okay, and that means that a dot b cross c is the n vector. Now after the area vector formed by this b and c vector is n vector. So the triple product is actually the dot product of this this area vector into this a vector. Okay, so let's assume that a vector, this is the a vector, any a vector, and this is the n vector. So the dot product of this a and n vector will give the triple product of a, b and c. So from basic mensuration that we learned in our mathematics in our school, that the area of base of any three-dimensional figure times the height h. So the area times h actually gives the volume of the three-dimensional figure. Okay, so in the similar way, a dot n is actually the multiplication. A dot n is going to be actually the multiplication of this a, magnitude of this a, the magnitude of this n, times cos theta. Okay, so a cos theta is actually the okay, yeah, okay, so a cos theta is actually the angle. Let's take this vector a and let's say this is n, so this is theta. Okay, this is a vector and this is n vector. So a cos theta is going to be this vector. This vector is a cos theta. This darker vector is a cos theta. So this darker vector a cos theta actually represent the height, and this n vector actually represent the area of this parallelogram. So that means that this overall combination will actually the volume of some figure. And what is that figure? Well, if we deeply look into it, then these three vectors, let's redraw this three vector. One is this B vector, this is the C vector, and this is the A vector. So in two dimensional, to figure out the area, we just transport this B vector over there and transport this C vector over there, and when the parallelogram formed by this B and C is defined by this B cross C. In the similar way, the dot product of the triple dot or scalar product of this three vector will represent the volume of a three-dimensional parallelepiped. Okay, so we will make a parallelepiped by this three. So this is the parallelogram formed by B and C, and parallelepiped can be formed by transporting this A vector over here and over here and over here, and transporting this B vector over here and C vector over here, and again B vector over here, and then C vector over here. So this is a three-dimensional figure which is called as the parallelepiped. So this scalar triple product actually represent the volume of parallelepiped formed by this A, B and C. So how can we write this A dot B cross C? Okay, so there is a way to write this. So what we know that like say this vector B cross C can be written as this way: x cap, if we are expanding that in the x the Cartesian coordinate. So this B is the bx, by and bz, and this is the cx, cy and cz. Okay, so their cross product will be let's say this is this is n vector, we have already assumed. Okay, so this is the n vector now. So that means we have n x component and then n x cap vector plus n y component and y cap vector and z component z cap vector. Okay, and n x component will be we have already seen our previous video that it is going to be b y c z minus b z c y, and similarly these terms will have their own formulas that we have already seen in our previous video. So I'm not going to write it again. You can go to that video and can see what will its values. Okay, so what we have to do it now. So B cross C will be this vector. Okay, and taking the dot product with A will give A x into nx plus a y into ny plus a z into nz. Okay, so instead of this, what we can also write over here: a x, a y, a z, and here we have the bx, by, bz. Okay, and here is cx, cy and cz. Why we are writing this? Because once we expand this, we will get the same this equation. Okay, as you can see that ax times, okay, so this is a determinant, the matrix we are actually this is a matrix and we are taking the determinant of this matrix. Okay, so ax and times by cz minus bz cy, and this is nothing but the nx. Okay, this is nothing but the nx term. In the similar way, the other term will be we will get. Okay, so in short, this determinant is actually representing the volume of the parallelepiped formed by this A vector, B vector and C vector. If this determinant is 0, okay, if this determinant is 0, that means that there is a 0 volume of this parallelepiped. That means that these three vector will lie on the same plane.